Welcome back. This is part 3 of optimization videos. In the last video we talked about steepest descent method. We looked at one problem and we talked about how we can get the direction, how we can get the lambda in the first step. Lambda was the length along the steepest descent direction. We went through the first cycle of finding lambda. This table right here shows basically 2 more steps. So just to recap, in step, let's say 0, we only have the initial guess. We evaluate the function at the initial guess, and that's 12. Remember, the function we had was right here on page 83. So that's the function. Well, this is the function, the objective function we have. We can evaluate it at 0, 0. You get 9 plus 1. So 9 plus 3 plus 2. So that's about 9 plus 5. That's about 14, I guess. And the table showed 12. Let's see, I think we made a mistake somewhere. So you put 0, 0 here. Then this is 9, and this is 3, and then plus 2. I think the objective function does not have this 2, so 9 plus 3, yeah, so most likely the objective function does not have this 2, so this 2 could be a typo there. But we're going to check. We're going to check for the next x. So anyways, so this is x naught, which is the initial guess. The second guess is going to be, we calculated here, it's going to be 3 halves, 3 halves. So this is 3 halves, 3 halves. We found lambda 3 halves. And then the direction was 1, 1. Right? So originally the direction was 6, 6. We normalize it to 1, 1 in a way that every element becomes 1. We found lambda. From lambda we got the next x. Now let's plug this in, we should get 5, so 3 halves, 3 halves. Let's go back to the function. So we plug in 3 halves, so that's basically 3 halves minus 3. That's 3 halves raised to the second power, that's 9 fourths. Now this one is 1 half. Raised to the second power is 3 fourths, so this is 9 fourths, 3 fourths. So that's about 12 fourths plus 2. I believe, yeah, I think the 2 is there. So 9 fourths is 3 plus 2 is 5. This is fine, but how come we get 12 here? Just let me double check. With x is 0, we have with x is 0 and y and x2 is 0. So we get 9 plus 3, that's 12, plus 2. That's 14. I think there's a typo here. This should be 14. I believe this is 14. Okay. Anyway, so now in the next step, we evaluate the gradient again. So this is the gradient evaluated at the most current point, which is 3 halves, 3 halves. So if you plug in 3 halves, 3 halves to the gradient, the negative of that is going to be this. You normalize it, becomes 1 minus 1. Just divide through by 3 here. Okay. And this is the direction. We solve the phi prime of lambda equal to 0. We find lambda equals 3 fourths. Then the next x is going to be previous x plus lambda times r. So this plus this times that gives you this, which is the next point. You evaluate the objective function at this point, you get 2.75. Now you have this point. We can go ahead and update our gradient again. So the gradient evaluated at this point is going to be that. Normalize it, you get this. Solve phi prime of lambda equals 0, you find this lambda. And then the next x is going to be the previous x plus lambda times r. You get that one. You evaluate the function again. So you see that the function is going down, but the step that actually goes down gets shrinked. Like here, the difference is 7. Here is about 2.25. Here is about 5 something. You see that? The difference is going down and down and down. So that means we're getting closer to the local minimum. Okay? So this example shows how you basically use steepest descent algorithm to find a minimum of an objective function. Okay, so in the next part of this video, now we're going to look at another method, which is Newton's method. So the issue with the steepest descent method is the pattern is zigzag. I mean, every time if you go back and look at the algorithm, every time, so this is basically an image of the progression of the steepest descent for some other problem. Anyways, if you look at this, you start from initial guess here, you go along the steepest descent direction, which is this red line, and you stop at a point, let's say gn plus 1 or xn plus 1, you stop at this point, and this is the length lambda we found through phi prime lambda equals 0 for the first step. Now in the next step, we find another direction. So the property of the steepest descent direction is that we always go along the gradient, and we know that the gradient is always perpendicular, to the constant line objective function. So if these are the contour lines of the objective function along which the objective function is fixed and constant, then the gradient is always perpendicular to that. So most likely, or maybe almost always, in the steepest descent direction, whenever we change the direction, the new direction is orthogonal to the previous direction. So because of that, in steepest descent algorithm, our path toward the minimum is zigzag. So that means we go along this up to a point that we actually change the direction. As soon as we change the direction, the new direction is going to be perpendicular to the current direction. So we're going to go this way, and then when we stop, the next direction is perpendicular again. So we go that way, and then this way, and that way. So you see that the pattern is completely zigzag. And that actually elongates or increases the number of steps that we can get to the point. So why not just go like this? I mean, it's like a curve. I think that would be quicker. So because of this zigzag pattern, we're going to look at the next method, which is Newton method. Newton method, this is very much similar to the Newton's method we did for one-dimensional problems. The only thing here is our function is a function of multiple variables. Okay? So in Newton's method, and the algorithm we had was the updated x, or the new x, is going to be the old x minus the function we want to find the root of. So what are we trying to find the root of here? Well, we want to minimize f, which means we want to set the gradient or the derivative of f equal to 0. And because f is multidimensional objective function, the derivative of that is going to be the gradient of that. So, okay, so in the Newton's method, instead of derivative of f, we're going to have the gradient of f. Okay. Now remember, in Newton's method, in the denominator, we had the derivative of what's in the numerator. Okay. If the numerator is the grad f, then the denominator is going to be the derivative of the grad, which means the gradient of the gradient, and that means the Histogen matrix. So in multidimensional case, Newton method takes this form of new x is equal to old x minus gradient of f divided by Hessian of f. Okay, and so to make it even clearer, let's look at the same example. We have objective function like that, right? x1 minus 3 raised to the second power plus 3 times x2 minus 1 to the second power plus 2. So here's the gradient of f we found before. Now what is Histogen matrix? Histogen matrix is you get the first row here and find the derivative of it with respect to x1, x2, and whatever we have. So the gradient of this, or the derivative of this with respect to x1 is going to be 2. The derivative of the same thing with respect to x2 is going to be 0 because there's no x2 in there. So it's going to be the second element 0. I'll go to the second row. Derivative of that with respect to x1 is 0 because there's no x1 here. And then the derivative of this with respect to x2 is going to be 6. So this is the Histogen matrix, okay, which is nothing but the second derivative of f with respect to existing variables. The first row, first index is just x. Second row, first index is y. First column, second index is x. And the second column, second index is y. Okay, hope this is not too confusing. Alright, so this is basically the gist of Newton's method. New x is going to be old x if you start from 0, 0. And the old x is 0, 0 minus inverse of the Histogen matrix. Okay, inverse of Histogen matrix. If this is a Histogen matrix, that's the inverse of it. And then times the gradient of f at 0.00. Well, this piece we recommended in maybe chapter 1 that we don't use inverse anymore. We use backslash operators instead of having inverse of h times f. For this step, we can use basically this vector, well, actually this matrix backslash this vector. So that's basically the same thing, but in a very efficient way. So instead of having h inverse grad f, we're going to have h backslash grad f. Okay, so we find the new x. We repeat this whole process again with this as the old x, then go and find another new x. Okay. So this was Newton's method. For the same example, let me see if I can show you the Matlab code corresponding to these. Alright, so this is the Steepest descent Matlab code. So we're going to quickly look at this and see how we can basically use Matlab to run Steepest descent. Okay, so we're going to have a function like main, and initially we have our standard clearing screen, clearing all the variables, and closing all the figures. For convergence, you put the threshold epsilon equal to 10 minus 10 to the minus 8, so this threshold is nothing but this epsilon that we had in the while loop. So this epsilon is right here in the steepest descent direction, or the steepest descent algorithm. Okay, so let's go back to the code. We always have the maximum iteration just in case if things don't work. We should have some safety knob to basically prevent our code, running forever. So that's the maximum iteration. Put at 20 for now. Initial guess is 0. Initial guess is 0, 0. First, I'm going to plot the function. So to plot the function, I'm creating an x vector and y vector from 0 to 4 for x and minus 1 to 3 for y with 50 points along the way. I'm going to create a mesh grid out of the x and y, so x and y vector. Then we create a mesh grid, so the capital X and capital Y now are going to be matrices. This is the function we had in the notes. Do the same thing. We want to optimize this and find basically its minimum. All right, so that was the plotting. You can go ahead and plot in 3 dimensions, x and y, and z is going to be the objective function. So if I put a breakpoint here, run it up there, then you should see this is the function. So it is pretty much like a bowl shape, you see that, and the minimum is somewhere around here. Okay, now we're going to draw the control lines. So control lines are nothing but lines of constant values of the objective function. So let me just comment on these. I only look at example 1, so I have to comment on these ones or comment these guys. Right. So put another symbol here. Okay. So now I'm going to look at example 2, now I'm going to look at example 3, we're just looking at example 1. So I'm going to put a breakpoint here, and then continue from there. So, from the top view, you see this is the bottom of the hole, and then these are the constant line objective functions. So objective function actually goes up or increases from here, going up, or going